Hey guys, let us now do some examples. Here we want to evaluate the double integral of the function 3x plus 4y squared over the following region R, which is the upper half plane bounded by the following circles. First of all, let us visualize the region R. Well, this is a region bounded by two circles, the smaller one of radius 1 and the larger one of radius 2, above the x-axis. Well, as we saw last time, this region is a polar rectangle. Namely, it consists of all the points whose polar coordinate r is bounded between 1 and 2, and the angle theta is bounded between 0 and pi. Well, remember, the double integral of a function f over a polar rectangle can be computed by turning it into an iterated integrals with respect to r and theta. So here, it doesn't matter which order we use for r and theta. So applying this to our function, we're going to replace 3x by 3r cosine theta and 4y squared by 4 times r squared sine squared theta. So here we have replaced x by its representation using the polar coordinates, and y by its representation in terms of the polar coordinates. In doing so, we replace dA by the term r dr d theta. So do not forget the additional r when doing this conversion. Since we have placed theta at the outer integral, this variable is bounded between 0 and pi, whereas r in the middle is bounded between 1 and 2. And the rest are just some calculations. So first, by evaluating the inner integral with respect to r, using the fundamental theorem of calculus, we're going to get the following antiderivative. And after evaluating at the endpoints, we get the following resulting integral with respect to theta. And finally, after some simplifications, we'll arrive at the final answer, which is 15 pi over 2. Alright, let us move on to the next example. Suppose we want to find the volume of the solid bounded by the following surfaces. First, we have the plane z equals 0, and second, we have the paraboloid given by the equation z equals 1 minus x squared minus y squared. Right, so let us first visualize the surfaces bounding the solid. Well, clearly, z equals 0 is the xy plane. And the paraboloid is an example of an elliptic paraboloid opening up towards the negative z-axis. So the highest point of the paraboloid is at the point 0, 0, 1. And the surface will be opening up towards the negative z-axis. Do you see that? So our region is bounded between the paraboloid and the xy plane. So here I have a better picture of the solid. Notice that the bottom surface of the solid is the disk of radius 1 centered at the origin. Well, you see, if we combine the two equations, z equals 1 minus x squared minus y squared, and the plane z equals 0, we are going to get this equation, which is the equation of a unit circle centered at the origin, which is the boundary of the unit disk given over here. Okay, let us call the bottom surface D. Also, the top surface of the solid is precisely the part of the paraboloid which lies above the x-axis. For a region like this, which is sitting on the xy plane, the volume can be calculated using a double integral. Namely, it is equal to the double integral of the top surface which will be a function of x and y coming from the paraboloid, over the bottom surface, which is the region D. And this bottom surface must be sitting on the xy plane. Right, before we compute this double integral, let us look at the description of the region D. Well, the region D is just a polar rectangle. Sorry, the R here should be D. In particular, this is a polar rectangle where the polar variable r is bounded between 0 and 1, and the angle theta is bounded between 0 and 2 pi. Next, let us compute the double integral by converting it into polar coordinates. Well, this is going to be an iterated integrals in terms of r and theta, where we have replaced dA by the term r dr d theta, and the function is replaced by 1 minus r squared. This is because 1 minus x squared minus y squared is equal to 1 minus bracket x squared plus y squared, which is 1 minus r squared. And the rest are just some calculations. Notice that the function here in the integrand does not depend on theta. So are the limits of integrations. So the entire inner integral is independent of theta. So if we wish, we can actually factor out this from the outer integral. And in doing so, we'll get the following product of two integrals. And this can be easily computed, so the final answer is pi over 2. Okay guys, that's all for now. See you next time.